Hey guys, this is Carrie, and this is the answer key for your homework assignment. So unlike normal, this one's coming from a lesson, because we had some really challenging problems in it, and I want to make sure we get to go over those. So we reviewed all this in class. Now, I'll just do these questions, all of them, I guess. So what is the period of this function? So because we have a coefficient on the inside, we know that in order for sine to completely repeat, the inside of that function has to hit a full cycle of 2 pi. So we set the inside equal to a full cycle. And now we divide by 4 pi on both sides, and we find that when x is 1/2, we will start to repeat. So that is the period. Wavelength is a term used frequently in science and mathematics. It is the length of one cycle of a wave before it starts to increase was the wrong word there. It really should have been repeat. Sorry about that. So if we think about the length of a cycle before it starts to repeat, here's one cycle. Then it starts to repeat, so here's the next cycle. So each one of these is called a wavelength. But we've seen this before. This is also called the period. Now there are some slight technical differences if you go on to study in science. Frequently think about period as a time and wavelength as a distance, but we're going to be using these words interchangeably in our class because when we're studying them mathematically, they really refer to the same quantity. So a sine function increasing through the origin, okay, so it's got to go through the origin. Sine function goes up, down, and then back to the midline. Can be used to model light waves. Violet light has a wavelength of 400 nanometers. So this will be 400 nanometers, which means that we can fill in the other tick marks. So you've got 200 in the middle, 100 here, and 300 here. So now this has to do with when is the wave decreasing. So to figure out when it's decreasing, you can trace along it. It looks like we're going up and up and up and up. And then when we hit this maximum value, we're going to decrease down to the minimum. So it looks like the function decreases on this interval and then begins to increase again. So from 100 to 300, we are decreasing. It looks like coordinates like x and y, but don't be mistaken. This is not x and y coordinates. It means from 100 to 300 on the x-axis. What is the maximum value of this function? All right, it looks like a tough question, but really, maximum value of the wave, that's going to be when it hits its top point. So the maximum value of this wave, it looks like, since the midline is 5 and the amplitude is 3, it looks like the maximum value is going to be 8 and the minimum value would be 3 below, which is 2, but we only wanted the maximum here. For number 5, I think I'll leave this one for you guys to figure out, but if you use a similar sketch to the one above, I know these are decimals. If you don't let that throw you off and use a similar sketch, you'll be totally okay on this one. Which function's graph has a period of 8 and reaches a maximum height of 1? All right, so I actually got this one wrong in class when I was working with some students, and the key word here is a maximum height of 1. So let's see how we do these. So first off, we can focus on the period of 8. So if it has a period of 8, that means that if we solve for the period here, figuring out what x value will turn the inside of the function into a full cycle, we should be getting 8. And we do. We get x equals 8. So the first two satisfy the period requirement. The last two are trap questions because we know that the period can't be 8 from here. The period actually is 1/4 pi from these two. So, okay. So now between the first two, how do we decide which of them which is the best choice? So if we look at graphing the first one, that will have vertical translation of -3, so the midline will be at -3. It's cosine, but it's -4, so it's going to start out 4 units below at -7. It's going to rise to the midline. It's going to rise the amplitude 4 units past this. So 1, 2, 3, and then 4 would be 1, and then down to the midline, and then back to where we started. So it does look like the maximum value is 1. So this one satisfies all the requirements. Now the thing to prove is that this one does not. So let's see about this one. So number 2, if you graph it, it has midline 5, 1, 2, 3, 4, 5. And the amplitude is -4, so it starts off 4 below at not -1, starts off 4 below at 1, rises to the midline, goes 4 past, which is 9, comes back down to 5, and then finishes at 1. And this one, even though it hits 1, it doesn't have a maximum value at 1. In fact, it has a minimum value at 1, so we have to eliminate that one too. Which of the following words is equivalent to the phrase average rate of change? So the average rate of change for a function is the slope. It's tempting to think it's one of these words, but these are wave-specific words, and we've been talking about average rate of change since Unit 1. This means the exact same thing as slope. All right, so for problem number 8, which of the following is the average rate of change of this function on this interval? So since average rate of change is the same thing as slope, we're allowed to bust out our slope formula. And the slope formula is y2, change in y, y2 minus y1, which is the change in y, over the change in x, x2 minus x1. So in order to use this formula to compute the slope, we need to find some values. So because we want the average rate of change from x equals 1 to x equals 3, what we're really looking for is the slope of the line connecting these 2 points. So the x values that we're considering are the ends of our interval, from 1 to 3. The y values we'll need to compute. To find the y values, we plug in the x values. So f of 1 is equal to 1 squared, which is 1. F of 3 is equal to 3 squared, which is 9. Using our slope formula, and I'm going to use the letter m for slope because that's what we often do. Slope is equal to y2 minus y1 divided by x2 minus x1. M is equal to 8 over 2. M is equal to 4. All right, so this is the theme. For the rest of the 2 problems, we're going to be doing the exact same thing. But things are going to get way worse because we actually have some pretty rough sine functions here. So the average monthly temperature in Buffalo in degrees Fahrenheit can be modeled by this function. And this problem is a regions problem. I'm not sure why they're doing this with the decimals other than to make sure that we have a really good calculator skills, where t is the month number. To state to the nearest tenth the average monthly rate of change. Hey, average monthly rate of change. That's the same thing as the slope between August and November. Explain its meaning in the context of the problem. So we're finding the slope. We want to use the slope formula. Change in y over change in x. Now, let's see. M is equal to... Oh, but we need values in order to do this. So our x values are going to come from the range that we were given, August to November. August is the 8th month of the year, and November is the 11th month of the year. So to find the temperature values that go with these, we can just put this all in on our calculator. B of 8 is equal to this crazy mess, 25.29 times the sine of 0.4895 times 8. Oh, that's not a parenthesis there, minus, and I'm just going to put dot, 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 because I don't think I need to write it all out in front of you. There's one thing you do need to be careful about, though, when you put this in on your calculator. So the first units that you learn for measuring an angle are degrees, but it turns out that the more natural way of measuring an angle is actually using radians. So if you don't explicitly say that you're using degrees in a problem, when you're creating a mathematical model, this angle here needs to be in radians. So what you want to make sure of is that the mode of your calculator, when you're doing a problem that doesn't explicitly say degrees, the mode of your calculator should be in radians. So we're going to go into radian mode. Okay, you can't see what I'm doing off to the side, but it's not that interesting. I'm literally just putting in 25.29 times the sine of 0.4895 times 8 minus 1.9752, close parentheses, plus 55.2877. And we get a nice long decimal here. I know some of you, Tommy, will be very happy to see decimals. I, on the other hand, wish the problem had been designed a little neater, but sometimes with real-world models, it doesn't always work out how you expect. So now for 11, we need to plug in the same thing. So I'm going to go into my calculator, plug in the exact same thing. And there's some quick ways to do that using second enter, but I can't show you at this point. But the number you get is 48.59796025. So now the calculation that we're going to be doing is y2 let me put it off over here, y2 minus y1 all divided by x2 minus x1. And you want to make sure that you put parentheses around your numerator and denominator, so you divide that whole numerator by that whole denominator. So let me type this in on my calculator. Sorry for the delay here. 0.59796025. And you should be getting m equals negative 11.0. Whoa, that's not the right answer. I read it wrong. Negative 10.08942.158. And they want it rounded to the nearest tenth. So m is equal to negative 10.1. And then they want us to describe the meaning in the context of the problem. So on average, because the y values had units of temperature, on average the temperature decreases by this is in temp and this is in months, so perhaps that helps. On average the temperature decreases by 10.1 degrees Fahrenheit every month, or per a month. All right, for this last one, this problem seems very crazy, but it actually comes from a real-life phenomenon. So you'll encounter this if you study physics, and I think it pays to see where this stuff comes from. So going on to Desmos here, I'm going to have to flip back and forth between them. We've got a basic function here, y equals 2 sine, that's not where that is, sine, and I'm going to have to go back to the notability page, 2 sine pi over 2x. And I'm intentionally leaving out the exponent because I want you to see why that exponent is important. Oh man, where's pi? Oh, there it is. 2 sine pi x, was that it? Pi over 2x, okay, so I'll fix that finally. And that gives us a nice sine wave. And let's say this was our sound wave, and I believe that that's the case that we're looking at in notability here. Yes, this is a sound wave. What this would say to me if I look at this graph is that this sound wave goes on forever. It never stops, so it's always ringing, which sounds like a new version of hell where there's just some sound always playing in the background. But luckily, sound doesn't do this. Sound eventually gets silent. And the way that you can model that mathematically is you can use exponential decay on your coefficient. And that's what this function is doing right here. So in the exponent here, it has negative 0.25x as the exponent. Let's see how our function changes when we add that part to the equation. So we've got to the, in parentheses here, negative 0.25x. And this actually is really what happens when you play a sound. The vibrations start off very high, and then they decrease, as you see on the right side, until they're basically quiet and not vibrating anymore. So by combining exponential decay, something we learned in the last unit, and a sine function, you get a sound function that decays over time, which is how sound really works. Now the thing you're being asked to find for this one is the exact same thing as we did in the last problem. We want the average rate of change of this function on this interval. So we have x, we have y, negative 7 to 7. To find the y values, we just plug in 7 and negative 7. So doing so on our calculator gives us 2 to the negative 0.25 times negative 7 times sine of second pi divided by 2 times negative 7. So when you plug in negative 7 here, you want to make sure you're plugging it in for both x's. You want to make sure you're in radian mode, and you want to make sure you're using parentheses so that things are where you expect them to be. So that gives us 3.3635856661. For f of 7, I'm going to do a similar calculation, but with 7 instead of negative 7. That gives us negative 0.2973017788 to compute the rate of change, we do y2 minus y1, all in parentheses, being divided by x2 minus x1, all in parentheses as well. So, oh wow, okay, so let's type this all in again. Last calculation of the problem set here, 3017788 minus 3.363585661. I hope I'm pressing the right buttons here. Divided by 7 minus negative 7. And that gives me m is equal to negative 0.26149196. And thankfully, rounded to the nearest hundredth, that is equivalent to choice 3. So I feel confident about my answers. If I made any mistakes, please make sure you email me and let me know. Hope this was helpful, guys. See you Friday in class.